current. DC output current is indicated by IDC. It means it is the average value of output current I. It is the average value of output current I. The waveform of output current I is shown in this diagram. Here, when the time period is from 0 to pi, diode is in forward bias. That means diode starts conducting, current is flowing. Then when the time period is from pi to 2 pi, diode is in reverse bias. That means diode is not conducting, so that there is no current is flowing through the diode. Then while I am explaining the operation of a half-wave rectifier, when the diode is in forward bias, I am replacing diode as a short circuit. But in practically, at the time of forward bias, the diode is operating a very small resistance. So the current through the diode or the current through the circuit at the time of forward bias, the maximum current flowing through the diode at the time of forward bias, I am writing as Im is equal to Vm divided by R plus RL. That means when the diode is in forward bias, diode offering a very small resistance, so that small resistance I am indicated by RF. RF is the diode offered by the resistance at the time of forward bias mode. So RF is known as forward resistance of the diode. Then RL is the load resistor. So the diode is in forward bias. The maximum current flowing through the circuit, or the maximum output current, maximum value of output current Im is equal to Vm divided by Rf plus Rl. Practically Rf is a very small value. Then when the diode is in ideal means diode is not offering any internal resistance. So I can put Rf as a 0 value. That means I can replace diode as a short circuit. So when I am short circuiting the diode, Rf becomes 0. So I can write Im is equal to Vm divided by Rl. So the DC output current IDC is equal to Im divided by pi. Remember this equation, average value of output current, or it is say DC value of output current indicated by IDC is given by Im divided by pi. The same way I can write the DC value of output voltage, VDC. DC value of output voltage is equal to Vm divided by pi. The next parameter is RMS output current. RMS output current, it is the RMS value, that means root mean square value. RMS value of output current I. It is the RMS value of output current I is given by IRMS is equal to Im divided by 2. Similarly, what is the value of RMS output voltage indicated by VRMS? RMS output voltage is equal to Vm divided by 2, half of the maximum input voltage Vm. Okay. So the third parameter is ripple factor. Okay, the output of the rectifier is not a stable DC. The output of the rectifier is a pulsating DC. That means the output of the rectifier contains DC as well as AC component. The unwanted AC component present in the output of the rectifier is called ripples. The ripple factor is a measure of amount of AC component. Actually, we are expecting that the output of the filter should be a stable DC one, but we can't achieve that practically because of the operations of diode. So a small AC component will present at the output of the rectifier. These unwanted AC components are known as ripples, and the ripple factor is a measure of amount of AC component present at the output of a rectifier. Ripple factor is indicated by R, which is the ratio of RMS value of AC component divided by DC component. It has the value of 1.221. Remember this value. Ripple factor of a half-wave rectifier is 1.21. Then the output of the half-wave rectifier has greater AC component because ripple factor have more than value 1. It has value of 1.21. It is greater than 1. So that means it is a high value. 1.21 is a high value. That indicates that the output of the half-wave rectifier has greater AC component. The next parameter is efficiency, indicated by eta, represented as a percentage. It is the measure of ability of a rectifier to convert input power into DC power. So the expression for efficiency, eta, is equal to 40.5 into RL divided by RF plus RL, where RL is the load resistor, RF is the forward resistance of the diode. Okay, then what is the next question is, what is the maximum efficiency that can be attained by the half-wave rectifier? The maximum efficiency is attained when the diode is ideal. Diode is ideal means diode has no forward resistance, that is RF is 0. So if the diode is ideal, RF is 0, so we can attain maximum efficiency of 40.5. So remember, what is the maximum efficiency of the half-wave rectifier? It is 40.5%. And what is the ripple factor of a half-wave rectifier? It is 1.21. Next parameter is peak inverse voltage. In abbreviation it is known as PIV. It is defined as, it is the maximum voltage appears across the diode in a rectifier when the diode is not in conduction. Okay, so again recollect the working of a half-wave rectifier. Remember, in working of a half-wave rectifier, when the input voltage is 0 to pi, when the input voltage is in the time interval 0 to pi, diode is in forward bias. That means diode starts conducting and a current is flowing. Then the time range is pi to 2 pi. Diode is in reverse bias. That means diode is not conducting. So that time I can replace that diode as an open circuit. So the PIV, peak inverse voltage, is what is the voltage developed across the diode when it is in reverse bias mode. So I am rearranging that equation. PIV is the voltage appears across the diode when the time limit is from pi to 2 pi. When the time is from pi to 2 pi, diode is in reverse bias. That means not in conduction. What is the voltage? What is the maximum voltage developed across the diode at that time is known as reverse bias, is known as peak inverse voltage, indicated by PIV. It is the maximum voltage appears across the diode in a rectifier when the diode is not in conduction. So in this example, in the previous diagram of a half-wave rectifier, diode is not in conduction. That means diode is in reverse bias when the time range is from pi to 2 pi. Okay, that time what is the maximum voltage across the diode is known as peak inverse voltage, which is given by peak inverse voltage is known as Vm. Okay, peak inverse voltage is given by Vm. That means maximum input voltage Vm. For the safer operation of diode, PIV should be less than breakdown voltage. That means breakdown voltage means for any electronic component, this parameter is there. What is the breakdown voltage? Breakdown voltage of a diode, breakdown voltage of a transistor, breakdown voltage of a Zener diode, like that. Breakdown voltage means it is the maximum voltage up to which the device can withstand. It is the maximum voltage up to which the device can withstand. That means consider a situation where it is stated that this diode has the breakdown voltage of 10 volt. That means if I am trying to apply more than 10 voltage to this diode, that is, if I am trying to apply 10 voltage, more than 10 voltage across this diode will damage. Okay, that is known as breakdown voltage. It is the maximum voltage up to which the diode can operate safely, or diode will operate safely, or diode withstand. Okay, so for the safer operation, the peak inverse voltage should be less than the breakdown voltage. So remember that point also. For the safer operation, PAV should be less than breakdown voltage. Breakdown voltage is the maximum voltage up to which the device, in this scenario it is diode can withstand, is known as breakdown voltage. Okay, so the next parameter is form factor. It is the ratio of RMS value to the average value. It is the ratio of RMS value to the average value. So F is equal to IRMS divided by IDC, or I can say F is equal to VRMS divided by VDC. This statement is also correct, but I will get in both case I will get the same answer. So IRMS is Im by 2, IDC is Im by pi. So finally I will get the form factor is 1.57. Remember this value. Form factor of a half wave rectifier is 1.57. Then what is the significance of this form factor? Form factor is a measure of smoothness of waveform. The smaller form factor indicates that greater smoothness. That means it has lesser ripples. Greater smoothness means it has lesser ripples or less variations. So the form factor is a measure of smoothness of the waveform. Then what is the ideal value of a ripple factor? Okay, ripple factor. What do you mean by ripple factor? Ripple factor is the measure of amount of AC component present in the output of a rectifier. Okay, it is the measure of AC component present in the output of a rectifier. Okay, actually we are interested to get no AC component at the output of the rectifier. So the ideal value of the ripple factor, we are expecting there should be no AC component at the output of the rectifier, but this is not practically possible. We are expecting like that. So the ideal value of the ripple factor R is 0 and the form factor F is 1. And the next parameter is peak factor. It is the ratio of peak value to the RMS value. Peak factor is equal to Im divided by IRMS. Also peak factor I can write Vm divided by VRMS also. In both case I will get the same answer. Im then substitute the value of IRMS. IRMS is Im by 2. So Im divided by Im2 equal to 2. So the peak factor of a half wave rectifier is 2 and the form factor of a half wave rectifier is 1.57. Don't confuse with the form factor and the peak factor. Form factor is ratio of RMS to average value. RMS to average value. And the peak factor is the ratio of peak value. That means maximum value. Peak value to the RMS value is the peak factor, which is 2. And the next parameter is transformer utilization factor, indicated by TUF. It is the ratio of DC output power and AC rating of secondary winding. Okay, it is expressed in volt ampere. It is expressed in volt ampere VA. So TUF is equal to final expression. Here I am writing only the final expression. TUF is equal to 0.286 multiplied by RL divided by RF plus RL. So the next question is, what is the maximum transformer utilization factor attained by half wave rectifier? How to get the maximum TUF? By setting RF equal to 0. That is, the maximum TUF can be attained by utilizing or by using the ideal diode. For an ideal diode, the forward resistance is 0. So setting RF equal to 0, you will get maximum transformer utilization factor is equal to 0.286. Next, we are going to see full wave rectifier. Okay, full wave rectifier is divided into two types: center tapped rectifier and the bridge rectifier. Okay, so first we will explain. First, I will explain the working and the feature, the circuit diagram, and the working of center tapped rectifier. In the center tapped rectifier, it consists of two diodes. In the figure, we can understood that it consists of two diodes. It consists of two diodes, and also it utilizes one center tapped transformer. That is why it is known as center tapped rectifier. It utilizes or it uses center tapped transformer. It utilizes center tapped transformer. Then I will explain what is center tapped rectifier. So it utilizes center tapped transformer. So what is center tapped transformer? Center tapped transformer means in a transformer there are two windings, primary and secondary winding. In center tapped transformer, the secondary winding is divided into two halves. And the common point of these two portions is grounded. Look onto this diagram. Secondary winding of a center tapped transformer. The one there is two halves are there, and the midpoint of these two halves is grounded, that is zero potential, and the voltage across the one half is indicated by VA, and the voltage at the second half is indicated by VB. Okay, so here I am writing that this one, the primary winding have N1 turns, and the secondary winding in center tapped transformer, secondary winding is divided into two halves. First half has N2 turns, the second half has also N2 turns, both having N2 turns. Okay, then next feature or next speciality of center tapped transformer is if center tapped of secondary, that means midpoint, if the midpoint of secondary is grounded, then voltages VA and VB becomes equal in magnitude but opposite sign. So that is here VA is equal to VB, but they are in opposite polarity. Okay, that is one more feature or one more specialty of a center tapped transformer. In center tapped transformer, secondary winding is divided into two halves, and the midpoint of these two halves is connected to a ground potential, and voltage across these two halves are equal in magnitude but opposite polarity. Here voltage across each half is indicated by VA and VB. These are equal but in opposite polarity. So that is why I am writing here VA is equal to minus VB. Okay, so in primary winding I am applying input to the primary winding is a pure AC signal. That is, for example, it is a sinusoidal signal. Okay, then it is a step down center tapped transformer, so magnitude is reducing. Then the voltage across the VA and VB also, it is also a pure AC signal, is in the form of sine wave, is in the form of sinusoidal signal. The voltage across the VA and VB is also a pure AC signal. So I am representing if VA is equal to the common method, usually we are representing AC signal in the form of a sinusoidal expression. So if VA is equal to Vm sine omega t, so I can write what is the value of VB, voltage across the second half at the secondary winding, is equal to minus Vm sine omega t. Okay, these two diagrams, diagrams of VA and VB is shown in the right hand side. First is VA. VA is a pure AC signal, is in the form of a sinusoidal. Okay, this axis is omega t. This is also a omega t. Okay, then VA and VB are equal in magnitude but opposite polarity. That is why VB is written exactly opposite to the opposite shape of VA. Okay, when VA is positive, VB is negative. When VA is negative, VB is positive. Likewise. Okay. And the third diagram is an output waveform that I will explain. Okay. Don't worry about that diagram now. Now just to observe only the waveform of VA and VB, output waveform. I will explain. Okay. So here I am showing the waveform of VA and VB. Okay, next I am going to explain the working of a center tapped rectifier. So in center tapped rectifier, similar what we are did in the working of half a rectifier, same procedure here also. Here I am splitting the time range in the VA waveform. The VA waveform is given to the diode D1, VB voltage is given to the diode D2. Okay, so this time limit is pi and this is 2 pi. Okay, similarly in VB this is pi and this is 2 pi. So I am splitting the time interval when omega t from 0 to pi. When omega t is from 0 to pi, then look on to this figure or waveform of VA and VB. When the omega t is from 0 to pi, what is the polarity of VA? VA is a positive value, and the omega t is from 0 to pi. VA is positive value, VB is negative value. VA is positive value, VB is negative value. Okay, then VA is given to the diode D1, VB is given to the diode D2. Okay, VA is given to diode D1, VB is given to diode D2. So when the time is from 0 to pi, VA is positive. That means VA is positive. That means D1 is in forward bias condition and D2 is in reverse bias condition. Here VA is positive value. So I can say here D1 is in forward bias mode. That means D1 starts conducting and VB is negative. So D2 is in reverse bias condition. That means it is a non-conduction state I can say, otherwise it is a off state I can say. Okay, when VB is negative, D2 is in reverse bias mode. That means diode is not conducting, or I can say diode is in off mode. Okay, so now we are in this situation when omega t is from 0 to pi, only D1 is in forward bias mode. That means only D1 is on condition. Okay, so I am at this scenario, just I am drawing the diagram, only the one portion. This is secondary transformer, midpoint is grounded, then D1 diode is in forward bias, so simply I am short circuit. For an ideal diode I can short circuit. Then the D2 is in reverse bias. That means for an ideal diode, reverse biased mode, at the time of reverse bias I can open circuit. So I am open circuit, then the load resistor is connected. Okay, fine. And then this is load resistor RL. Here D1 is there. At the D1 is diode is in ideal one. So the ideal diode can be replaced as a short circuit when it is in forward bias. And this is D2. D2, an ideal diode can be replaced as an open circuit mode when it is in reverse bias. Okay. So now the D1 is in on condition. So a current is starts flowing from like that. Current is starts flowing like that. So this current is indicated by I. Okay, so first time interval when omega t is from 0 to pi, diode D1 only conducting, then so that a current starts flowing through the diode and to the load resistor RL. Okay, and the voltage, this voltage is VA. This voltage VA is appears across the load resistor. Actually this is V0, output voltage, which is same as VA. Okay, because look onto this diagram, because the RL gets connected to the node A. This is node A. The RL gets connected to the node A through the diode D1. D2 is not conducting, so in this situation leave D2, concentrating only the diode D1. RL gets connected to node A through the diode D1. So I can say the output voltage, that means voltage across the load resistor RL, that is indicated by V0, which is equal to VA. Okay, then the next time limit, when the omega t is from pi to 2 pi. Then again look onto the previous diagram. When omega t is from pi to 2 pi, VA is negative and VB is positive. When VA is negative means D1 is in reverse bias condition, that is off mode, non-conduction state. Then VB is positive, that is D2 is forward bias mode, that is on condition, on state. Okay, so I am drawing the figure. And the midpoint of the secondary event is grounded, and the D1 is reverse bias, assuming that diode is ideal. So at the reverse biased condition, I can open circuit. Then D2 is short circuit. An ideal diode can be short circuit at the time of forward bias condition. And the load resistor. And this is RL. Okay. And the current is flowing like that. Okay. Or in the reverse manner also, path is like that only. So the output voltage is indicated by V0. Okay, is equal to the output voltage V0. I can write the output voltage V0 is equal to VB. Okay, the output voltage V0 is equal to VB, because here only D2 is in forward bias mode. The load resistor RL gets connected to the node B. This is, let it be, this is node B. Connected to the node B through the diode D2. So VB appears across the load resistor RL. So I can say V0 equal to VB. Okay, so that's why now observe the waveform of V0. V0 is VA when the time limit is from 0 to pi, and the V0 is equal to VB when the time limit is from pi to 2 pi. Okay, so the output waveform, that is voltage across the load resistor, have the shape as shown in the figure. Okay, then by observing the waveform, output waveform of center tapped rectifier, I can say that the full wave rectifier is a combination of two half wave rectifiers. Full wave rectifier is a combination of two half wave rectifiers. Okay, so this is the operation of center tapped full wave rectifier. So I will summarize the operation. Center tapped rectifier consists of two diodes, and why it is said to be center tapped? It has a center tapped transformer in center tap transformer, the secondary winding is divided into two halves and the midpoint of secondary winding is grounded. So the voltage at each half of the secondary winding is equal but in opposite polarity. This makes diode D1 starts conducting at one time and D2 starts conducting in another time. That means D1 and D2 are not simultaneously conducting. At the time of 0 to pi, D1 conducting, and the time range omega t from pi to 2 pi, D2 conducting. So the output waveform looks like combination of a two half-wave rectifier. So this is the operation or working of a center tapped full wave rectifier.